Guys, my name is Vincent, and I'm going to take you through the recent statistical machine learning report. This report was divided into two parts. The first part involved working on the SML dataset, and just a brief size of the dataset. This dataset had 225 rows and 2 columns, and just plotting a scatter plot of the distribution of x and y reveals not so linear pattern, because and it's quite clear that moving forward it will be impossible to capture the relationship between the variables using just a simple linear model. And so given that y is continuous, we can choose to settle on regression, because regression is suitable for these tasks. Now part 2, for the theoretical framework. It's a lot of theory, so I'm going to just mention it is in passing. So the function space, the input, the input space, and settling on the appropriate loss function as the mean squared error, or popularly known as the L2 loss function. And also the theoretical risk, the Bayes learning machine, the empirical risk and model complexity, deriving the OLS estimator for the empirical risk, a few properties of the empirical risk: unbiasedness, efficiency, sensitivity to collinearity, dependence on the basis functions. I'm going to go straight to the cross-validation, and just after performing the cross-validation, you can see from the graph that the optimal polynomial has degree 12. It's the polynomial that we can get the perfect bias and variance trade-off. And just to move to the next plot that compares how each of the different models fits our data. The simple model, it's degree 1, so it's just a straight line. The optimal model, it tries to fit the data well. It's of degree 12, and the complex model, it's clear from the graph, but it's trying to remember the patterns in the data. And to just move to the box plot for the analysis, it just reveals the same pattern. The simplest model has the highest test error, followed by the complex model, and finally the optimal model has the lowest test error. And just to do a further analysis using analysis of variance, we get a very low p-value that indicates that these differences between the models is statistically significant, indicating that we can actually conclude that the optimal complexity is degree 12. And for the confidence and prediction bands, we can see from the graph, the three graphs, that the the margins, or the width of the confidence bands in the simple model and the complex model, they look very different from the optimal model. And this is the mathematical expression for the prediction band and the confidence band, and just several conclusions that we can draw from the confidence bands and the prediction bands from the complex model and the simple model. And moving on to the SPAM dataset, this is a dataset that is inbuilt in R, in one of the libraries in R. It's about predicting the probability of an email being a spam message. So just a brief overview: the data has 4,601 emails. Some of them are spam from the graph. The non-spam are a little bit higher than the spam emails, showing a slight imbalance. Some of the variables, predictor variables, are word frequency, character frequencies. It's very high dimensional. It has 57 variables. Most of them are continuous, but it's interesting because the variable that we are trying to predict is binary. So this is a classification task, and The models that you are going to use, the FLD, LDA, QDA, and the naive Bayes. Uh, both of them are, all of them are classification models. So the I'll say the objective of this task is to prove the Occam's principle that says simple models always perform the best. And looking from the comparative ROC curves and from the box plot, it is clear that the two models that perform the best, LD and FLD, uh, are they have the lowest test error, indicating that simpler models always perform the best compared to QDA, which is very complex and it has a slightly worse test error. So from this exercise 2, I'll conclude that simpler models are always the best.